Okay, so let's move to the tools that are used to study the eigenvalues of random matrices, of Hermitian random matrices. Let me hide this thing. Okay. Okay, so let's say that we have random matrices. So what we care about is not a specific instance of a random matrix, but rather the distribution over matrices. And let's say, for instance, that we have random matrices whose coefficients are drawn from a Gaussian distribution with mean zero and a given variance, and this matrix is symmetric, all the coefficients are real, and besides the fact that it's symmetric, all the coefficients are independent. So given one realization of this matrix, what we can compute is, we can compute the eigenvalues, and we can define an empirical spectral distribution, which is basically just a sum, a combination of delta functions entered into the eigenvalues of the matrix. So the spectral density is defined as the average of this quantity over the distribution of matrices. An important property of random matrix in general of disorder system is called self-averaging, which consists in the fact that if when the size of the matrix goes to infinity, under some condition, if the ensemble is self-averaging, the empirical spectral distribution converges to the spectral density. It's important to underline that in most of the matrices, we actually, in the entirely set of matrix ensemble we will study in this course, this condition will hold. But in general, this is not true. And actually, a good exercise is try to find a random matrix ensemble for which self-averaging does not hold. Okay, so if self-averaging hold means that the empirical spectral distribution, so if we have a very large random matrix, its spectrum, the histogram of its eigenvalues will converge to the distribution over matrices of eigenvalues, computed averaging over matrices. Okay, so sorry, let me go back. So in principle, if we want to solve this problem, we should be able to compute the average in equation 10. But of course, as you expect, averaging over matrices, combination of delta function, is something that is typically hard. So we're gonna do a trick, and the quantity we're going to introduce is called resolvent, which is defined as in equation 12 as the integral, as the average of 1 over z minus the eigenvalues. And assuming that this quantity is self-averaging, we can compute this quantity simply summing over the eigenvalues. So in equation 12, we have a sum over an average over the empirical over the spectral density. So where we averaged the eigenvalues over the distribution of the matrix ensemble. In equation 13, instead, we have one matrix that is very large, and we are computing this quantity for one single matrix. If self-averaging holds, then these two quantities are going to be the same. So this quantity is a central object in random matrix theory, and in general, if you're going to work on random matrix theory, you're going to spend almost all your time trying to compute the resolvent. Okay, so the reason why we care about the resolvent is that from the resolvent we can go back to the spectral density. So simply using these known property of the delta function, we can invert the definition of the resolvent and obtain the resolvent from the spectral the spectral density from the resolvent. So the resolvent can be used to compute the spectral density, but can also be used to study the properties of the eigenvectors. So let's say that we have an Hermitian matrix. We can decompose it as in equation 16 over the eigenvalues and eigenvectors. And in general, we can define the following matrix simply by summing over the inverse of the elements, simply by computing the inverse of the matrix plus a diagonal, and the resolvent is simply the trace of this quantity. So in general, in a similar way, we can write that these diagonal elements of this resolvent matrix are the composition with the on the eigenvectors, and by doing a few calculation, we can rewrite it as the spectral density and the eigenvectors, the components of the eigenvectors corresponding to a given eigenvalue. And then simply by using again the properties of the delta function, we can invert this expression and obtain what are the expected values of the components of the eigenvectors associated with given eigenvalue lambda. Okay, so this concludes the second part, where we define what is the resolvent, and we define how to obtain the spectral density from the resolvent, and now to obtain properties of the eigenvectors from this quantity.